2B1 span 2. So, pininga beam is continuous, no? Continuous sila over 2 spans. So, nagsumpay sila dire, di ba? Continuous sila dire ng 1. But is continuous on this side and is continuous on this side. So, we calculate the span for 2B1 span 1 and 2B1 span 2. Nakadaling calculation na to. So, again, pwede siya katong center to center for distance towards the column. No? And assuming a column dimension of 0.4, so we add half the column dimension, so plus 0.2, and we subtract the girder width, which is assumed to be 0.3, and subtract half the girder width on this side. So the girder width is 0.3, and half of that will be 0.15, and we get the span of 7.75. Now for this beam, it's simply the center to center distance minus half the girder width here and minus half the girder width here. That comprise 2 half girder widths, and therefore will amount to a full girder width minus 0.3. Okay? Well, minus 0.15 minus 0.15 again. No? So don't bother about those numbers. No? Hindi mo pagkita pero hindi mo sana nakuha. The idea there is you compute or determine the clear span. Clear span. Okay? Ako na siya niya ang punto na ng calculation. Don't bother too much on the details. First, you understand what is being computed. Yeah, wala na, may bawa na kung saan mo pag-compute, no? Plus or minus naman sa mga dimension. And in the next step, we have here the requirement, no, for the minimum depth of the beam for deflection control. For one end continuous, we have L over 18.5. So L is, we will use the longer span, 7.75. Actually, kinisi yung kini mo tayo bigger, no? So kanila itong gamiton, with by 18.5, we get 419 millimeter. So this is the code prescribed the minimum depth of the beam in order to control deflection. However, ang atong i-assume na rin beam size, atong himong 300 by 600 millimeters. Of course, at this point sa atong pag-compute, kung matakaibaw kung kana siya dako ra ba o kana siya gamay ra ba, no? So that is just an assumed size, and don't be afraid to assume a size. Just assume a reasonable size, no? Hindi kayo dako, bisa kayo gamay, diba? So, sana hindi kayo dako, hindi kayo gamay, tinali maklaro para ninyo kay mo kumay lagi pag-design ninyo, no? But as you gain more experience in designing, then you'll be able to assume a reasonable size. Of course, iterative na procedure na siya, no? Simple rin assume na size, nakura, you will know that later as you finish your calculation, then you have to revise, no? Nalitan mo yung assume na size, kamay na saan, may bawaan na saan mo, no? Kaya mo saan nag-revise. Kakalitan mo yung sobra na kadako, isa't mo yung sobra na kagamay. Sa kapage, no? Nakapag kaya classmate mo nga mawawala ng design data, isang nga mag-compare mo, no? Yan span 8, yung 7.5, at hindi siguro kayo maglayo ang inyong sizes. Pwede isang mo nga tinabangay, no? Tinabangay sa inyong pagkuhan, pag-solve. So, wala ka itong i-assume na size nila sa atong i-present na computation, 300 and 600. So, from that, we compute the effective depth. We have the depth of the beam, 600, minus the protective cover, 40, then minus the diameter of the stirrup, then minus half bar diameter. So assuming a bar diameter of 25 millimeter, then half of that will be 12.5. Okay? So balik ko na ko, pagkaling 40 protective cover, this is the stirrup diameter, 10 mm. Then 12.5 is half the bar diameter. Of course, kung sa tagaibaw ni kung pila yung diameter sa bar na itong gamiton, so just assume a size. So 25 mm will do. No? So we get the tentative value for the effective depth equal to 527.5 millimeters. So mana na atong i-compute rin ang dead load. So the dead load consists of the beam weight. We have the dead load coming from slab 2S1 and dead load coming from slab 2S2. So for the beam self-weight, that is unit concrete multiplied by the dimension of the beam, 0.3 by 0.6 meter. Then for slab left dead load coming from 2S1, we have already computed that from the slab design. So mag-design of the slab, you compute the load transmitted to the supporting beams as preparation for the design of the immediate or interior beams. Then slab right load coming from 2S2, ato na siya nakuha ikan sa design sa slab. Okay? Ato na lang ang i-apply na yung diri karon. 9.27 kN per meter, 7.94 kN per meter. So the total uniform load supported by the beam is simply the sum of these three to get 21.46 kN per meter. Then for the live load, so we have the slab left live load coming from 2S1 and slab right live load coming from 2S2 for the mga answer. And in addition to that, we have the live load directly, which is placed directly on top of the beam. No? So we assume a live load of 4.8 kilopascal. So multiply that by the width of the beam. Okay? Which we assume to be 0.3. Kahit kaning sa slab na, remember that in computing the load of the slab, we use the slab beam span. Atay live load, yun yung apply sa slab, but we have to take into account also the live load directly on top of the beam. No? So that's the uniform live load of 4.8 kPa times the assumed beam weight of 0.3. So we add this, we get a total of 18.09 kN per meter. So these are what we call the service load. And since we will use the ultimate split design method in the design of the beams, then we compute what we call the factor loads. So we just multiply dead load and live load by their load factors. Okay? So parehas sa slab, take note na natong load factor na gamiton, instead of 1.4, we use 1.2, and instead of 1.7, we will now use 1.6. Because those are the updated load factor as prescribed in SCP 2015. So, next we add the factor dead load and live load to obtain the total factor load. So once we have the total factor load, then we apply the SAI moment coefficients for continuous beams and one-way slabs. No? So sa may moment coefficient rin. Sa discontinuous end, you have 1 over 24 WL squared. Mid span, correct, no? So 1 over 14 WL squared. Then at the interior support, you have 1 over 9 WL squared. Ay duha naman yung span, no? So 1 over 9. Okay, so nasabda na to. Ito na to ni asa na to ikuha ng 1 over 24, 1 over 14, 1 over 9. Sa interior support, you use the average of the adjacent spans. No? So 7.75 plus 7.7 divided by 2. Kasi yan ang average span. So para ito ma-determine ang mga design ng mga bending moments, and we calculate the steel reinforcement. No? So negative steel at the discontinuous end, meaning 152.13 kN per design moment. Then we compute the steel using the formulas we have learned from reinforced concrete design. No? Ito na pong RU equals MU over 3 RUB BD squared, no? Then approve formula AS equals rho BD, then select the bar diameter and compute the area of the bar, then divide the required area by the area of the bar. We have 1.62 gram of 2 pieces of 25 mm diameter bars. Now for steel reinforcement midspan. So at midspan, the bending moment is positive, and you have this slab at the compression side, no? So this will act as a T-beam. So sa reinforced concrete design, nag-discuss naman ng T-beam, di ba? Discuss na, no? Yung next one discuss na pag-best teacher, yung RC design. So inawag kayo itong hinduman. Kailangan sa itong lecture notes niya, in case you already forget. Para tayo na calculation ni mo on, no? Sa lecture notes. No? So ato pa ito lang we write the solution in detail in this design calculation. So kay T-beam action man, we have to compute the effective flange weight. According to the code, it's not to exceed 1/4 of the span, not to exceed BW plus 16 times the slab thickness, and not to exceed the centimeter spacing between beams. Ang ginagagamay ni Tulo, ano siya govern sa yung effective flange weight, no? That will take part in the compression action. Manana, we compute the trial steel area using this formula. So MU, that is the design moment at midspan, Fy the effective depth, T is the thickness of the slab, no? Then we have given the depth of the construct, A is equal to A sub 1.25 C prime B. Then the coefficient RU was MU over PBD square, then steel ratio over O. By the way, importante ganun, no? Pag compute na to sa A, we compare whether A is greater than T or less than T. Diba? If A is less than T, then you have a singly reinforced rectangular beam analysis with a weight equal to the effective flange weight. If your A is greater than your T, that means the depth of the compression block goes below, no? The depth of the slab, so it will be a T-beam analysis. But in this case, if A is less than T, therefore siya T-beam analysis, no? We have only singly reinforced rectangular beam analysis. Now, this usually happens because your slab is so wide, you know, effective flange width niya is, based on the calculation there is 1,938 millimeter. That will usually confine the depth of compression block within the slab. No? Gawa siguro sa mga simple supported mga beam, kung bending moment sa midspan, kaya ka ng isolated na T-beam, hindi kayo lapadan yung flange, ang imong depth sa compression block mo naog, no? Ito sa beam wet. Pero kasagaran sa mga reinforced concrete floor na ingon ini, usually we get A less than T. So kung A less than T, kung sa ito ang calculation, hindi man T-beam analysis ang giginahanglan, no? You just continue applying the formula for singly reinforced rectangular beam. RU, rho, then this is less than rho minimum, so we complete 4/3 rho, then we use the smaller between 4/3 rho and rho minimum. So what is required steel area, then we divide by the area of 25 mm diameter, 10.57, and we round off to 4 pieces of 25 mm diameter parts. Wala ba pangutana? Wala ba question?